This video is about sampling. If you recall, statistics is about sampling. Our goal is to make inferences about the population from samples because it's very difficult for us to have access to the entire population with some rare exceptions. So we generally make inferences using statistics, make inferences of population parameters. So today we're going to talk about sampling. So a sample is a subset of n elements taken from the population, from a population of what? Population could be people, can be non-human animals like parrots, or inanimate objects like, I don't know, marbles, geographic units, whatever. It's a sample. The population includes all possible elements with the characteristic of interest based on factors such as, for people, could be something like ethnicity, like we could be focusing on all Hispanics. If we look at education level, we could be looking at all individuals with a high school education or less, income, all individuals making greater than 100,000 per year, etc. So that's what the characteristic that define our population is. The population, we call the population, which is defined by the characteristic of interest, the sampling frame, the sampling frame. So an example, a study of depressive symptoms among adults 18 and older with a high school education or less in Pennsylvania. Our sample frame would be all adults in Pennsylvania, 18 and older. Sorry about that. 18 and older with a high school education or less. We collect data from a subset of individuals, and n here represents number, right? A subset of n individuals because we cannot, like I mentioned, we cannot collect data from everybody in the entire population or the sampling frame. And the reason we can't do that is, well, it's many. We don't always have access to the entire population. Like, for instance, if I'm dealing with high school students, I may not have access for legal purposes to the names and addresses and phone numbers or contact information of all high school students. Cost, it's extremely expensive to do that. And times, and that, I mean, the amount of time it would take to have access to every person in the population would be just crazy. So our goal is just to make inferences about the population from the sample. One of the issues that we have in terms of sampling is to figure out, excuse me, what is the appropriate sample size? So what's the sample size appropriate to achieve our goal? And our goal is to reject the false null hypothesis. So we can do that using software, or you can actually sometimes calculate these by hand. We can estimate our sample size. So what we want to do is we want to estimate our sample size so we have a large enough sample size to confidently reject a false null hypothesis. So that's our goal. We want to be able to reject, and the probability of rejecting a false null hypothesis is power. So what we're trying to do is have enough power with our sample size to achieve our goal, which is rejecting a false null hypothesis. So here's some terms or some elements you need in order to estimate power. Estimate sample size. You need power. You need an alpha. So alpha is the probability of a false positive result, or what we call a type 1 error. False positive would be something like rejecting the null hypothesis when we shouldn't have rejected it. We need an effect size. An effect size is a standardized measure of effect. You think about what's the effect of a drug on something like happiness. I mean, what would we consider having a practical effect? Like if I take a person who's already happy and say our happiness score ranges from 1 to 100, and I raise them from, I don't know, 80 to 81, is that meaningful in any way? Maybe if we raise somebody's happiness score from 50 to 75, that would be more meaningful. So we standardize those effects into small, medium, and large. We'll talk about those later, but you do need to have an understanding based on what you read in the literature, what you expect to find when you're conducting a study. Do you expect to have a small, medium, or large effect? And then, of course, you need software. Software, you can estimate sample size. Software, there's different kinds of software. I use something called Gpower. I believe I'll be talking about that shortly, but you can also estimate sample size by hand for tests like the t-test and the z-test, or even confidence interval in many intro stats classes, depending on how crazy your professor is. She or he will make you do that. All right, let's talk about hypothesis testing. Should be a review, I hope, because if you're, especially if you're in a research methods class, you have to have had stats already. If not, well, introduce you to it. There are two types of hypotheses. We have the null and the alternative hypothesis. This is, of course, assuming that we're doing null hypothesis significance testing. Okay, so there are other ways of doing statistics that do not in, do not involve or appreciate the null and alternative hypothesis, like Bayesian statistics. All right, so let's talk about our alternative hypothesis. That's actually our research hypothesis. That's the hypothesis we desire to support. That's the one we were interested in. See, when we think about doing research, we think about what we want. We don't think about what we don't want. But we have to think about what we don't want in null hypothesis significance testing. So here's an example of an alternative hypothesis. 3 sets of squats 3 times per week improve ski racing performance as indicated by time down a ski race course, or exercising 3 times a week for at least 20 minutes per session decreases the risk of type 2 diabetes. So those are the things you'd like to show when you're doing research. The null hypothesis is the hypothesis we would like to reject in favor of the alternative hypothesis. So I mentioned null hypothesis significance testing. So in NHST, using the acronym, we always assume the null hypothesis is true. This is something that the Bayesians don't support or agree with. So we conduct studies to see if it is possible to reject the null hypothesis. Here's examples of our null hypotheses that line up with the alternatives that I just read out. 3 sets of squats 3 times per week does not improve ski racing performance as indicated by time down a ski race course. Exercising 3 times a week for at least 20 minutes per session does not decrease the risk of type 2 diabetes. So we assume that these are correct when we start the study. We don't assume that our research hypotheses are correct. So here's an example, something you can work out on your own. Imagine you're interested in the relation between CBT, cognitive behavioral therapy, and social anxiety disorder. Your research question is, does CBT once weekly reduce social anxiety symptoms in young adults age 18 to 24? So that would be like a research question. You'd want to write down your null and alternative hypothesis for that. Okay. Something to practice on your own. Let's go back to the hypothesis testing and the outcomes of our hypothesis test. So there are 4 possible outcomes in a hypothesis test. There's a true state of affairs that somebody knows we don't know, or the universe knows. The null hypothesis is true or the null hypothesis is false. There's also our decision. Either we reject the null hypothesis or we fail to reject the null hypothesis. So this is going to be done based on the results of our data analysis. So if we reject the null hypothesis, but the null hypothesis is true, we've committed a type 1 error. So it's a false positive result, right? That's what alpha represents. Alpha is the probability of a false positive result. If we reject a null hypothesis and the null hypothesis is false, we have power. That's when we talk about power. That's the probability of rejecting a false null hypothesis. If we fail to reject the null hypothesis and the null hypothesis is true, we've done a good job. We have confidence. This is where confidence intervals come from, actually. Our sample does belong to some population. If we fail to reject the null hypothesis, but the null hypothesis is false, bad, 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 that's called a type 2 error, or beta. So confidence and alpha are complementary. So 1 minus alpha is confidence, 1 minus confidence is alpha. Power and beta are complementary. 1 minus power is beta, 1 minus beta is power. We tend to, for alpha is probably the most common probability that you deal with when you do statistics. Generally have to set your alpha, but you sort of have to set it. Most researchers don't set it. It just kind of is implied when they're doing their research. The most popular alpha is 0.05, and I'm sure from your experience in statistics, you know of this value because most researchers talk about it. And to reject a null hypothesis, your p-value has to be less than or equal to 0.05. Well, they may say less than 0.05, but this is not required. There's no law stating you have to use alpha of 0.05, and you can select whatever alpha you want. You're the researcher, right? So the rules I would follow here is if you're dealing with a relatively new study and there's no danger involved in your study, or you have a very small sample size, you can set your alpha at 0.10. This would increase your power. If, on the other hand, you have a very large sample size or there's some extreme risk to your participants, like say if you conclude that a drug works, but it doesn't work, and this drug is really dangerous, has extreme liver damage or something like that as a side effect, you want to make sure when you reject the null that you make it really hard to reject a null. You don't want any false positives. You decrease your alpha, but that also will decrease your power. With large sample sizes, we're overpowered, so it's better to reduce our alpha a little bit because we want to make it harder for us to reject a null. So let's talk a little bit about how alpha, the null hypothesis, and p-values are related. So in the null hypothesis is related to what we call the null population. So the null population is defined by the null hypothesis. So in this case, we assume that all samples collected belong to the null population. So they're members of that null population. None of them are different than a null population. So here's an example comparing a sample of freshman college students to the population of freshman college students nationwide on happiness. Our hypothesis is that the sample mean happiness is equal to the population mean of happiness. So again, sample, we use Latin letters and put that little bar over to indicate mean. And mu is a Greek letter that indicates a population parameter value, population mean for happiness. And our alternative hypothesis is that the sample happiness mean is greater than the population mean for happiness. So our null population is the population in which the sample mean does not differ from the population mean. So this is our null population. So you understand that in the null population, our sample mean does not differ. It doesn't have to be exactly equal. I think this makes it difficult for some people to understand. When I say it's equal, it doesn't mean that numerically it's equal. When we say it's equal, there's not enough evidence across samples that there's a difference between the sample mean and the population mean. And we're going to select what is required to indicate that there's a difference. But this equality doesn't mean that they're numerically equal. Like if happiness mean is 3.54 in the population, the sample mean would have to equal 3.54. That's not what this means. Let's pause on that for a minute. In this case, I just made a note that the alternative hypothesis is directional. When I talk about directional tests, what we have to deal with that at some point, we're looking at a specific direction in the nature of the relation between the two variables. In this case, our sample mean would be greater than, so this indicates direction. If it was non-directional, we'd say sample mean happiness is not equal. There's no direction stated. But once I state a direction either greater than or less than, that's what we mean by a directional hypothesis. And also that indicates whether we're dealing a one or a two-tailed test. If it's directional, like we're looking at one of the tails of our distribution, and this is our distribution, you'll notice that there are tails on each. We call these tails. Think of them as like dragon tails. So the two-tailed dragon, right? When we're looking at a single direction, either greater than or less than the mean, the population mean, which is indicated by this thick line right here, we're indicating a direction. So those are also known as one-tail tests. Okay. The p-value, we always talk about p-values when we're dealing with, excuse me, data analysis. Your computer packages spit out a p-value. So that's the probability of the observed value or greater. I'll say instead of or greater or more extreme, the observed value or more extreme, given the null hypothesis is true. So assuming the null hypothesis is true, what's the probability of this value, like our z-test value, or or more extreme? The reason I'm saying more extreme because see, sometimes our z values, so our z values are standardized, they're are standardized values. So our z values indicate standard deviations away from the mean. But if we're going in the negative direction, it'll be more negative, right? To reject a null, the p-value would indicate a value that's at our calculated z-value or smaller, right? When we're dealing with positive values, it would be a z-value or greater. So that's why I'll say more extreme. That indicates either negative or positive. Okay. So now if we were to take the, I wrote or greater here, if we were to take the absolute value of the z, then we can talk about it as uh, um, being something or greater. So assume let's just clarify what the p-value is. And let's assume for a second that we're dealing with positive values or absolute values so that they come out positive. With an absolute value, you're removing the negative sign. Assuming the null hypothesis, excuse me, assuming the null population is the true population, what is the probability of our standardized difference or greater? So when we say standardized difference, say like this is our sample, like sample two, right? It has a mean right here, and when we calculate its z-score, it would be the difference between here and here. So that's what we mean by standardized difference. Same like sample four, this is the difference, right? The standardized difference would be in a z-value. All right, so let's look at alpha and p-value. Alpha itself, if we recall, alpha is the probability of a false positive result. It defines the cutoff point, the critical value for judging statistical significance. So assuming standard normal distribution, I'll go through this very clearly, both reading what I wrote and then also explaining it. Assuming a standard normal distribution. So if you recall, a standard normal distribution, the natural parameters for the normal distribution are the mean and the variance, right? So with a standardized value, we have the mean of 0 and the variance of 1, or you might want to say standard deviation, square root of the variance. Assuming a standard normal distribution, and let's just for this case deal with alpha, that's the popular value of a type 1 error, right? Probability of false positive result. All z values greater than or equal to 1.645 would result in rejecting the null hypothesis, assuming also a one-tailed test, right? So let's take a look at that. So if we're looking at a one-tailed test, say our null hypothesis is there's no difference between the sample and the population. Our alternative hypothesis is that there is a difference between the sample and the population, right? But our alternative hypothesis is that the sample mean is greater than the population mean, so it becomes directional. So you'll notice in this figure that I have cutoffs on both sides. If I'm dealing with a directional hypothesis, I'm ignoring, and we're talking about the sample mean being greater than the population mean. I'm going to ignore the left side of this distribution. I'm going to look at the right side. I think I'll have an example later where we're dealing with the left side. Okay, so our alpha is 0.05, right? So that's the probability of a false positive result. That alpha cuts off the upper 5% of the distribution. The upper, so this is the most extreme 5% of the distribution right here, this white area, right? So this is telling us what our rejection region is, right? So any standardized value, let's say z value in this case, let's stick with the z. I mean, there are other test statistics as well. Any z value that is greater than or equal to 1.645 would have a probability of occurring at 5% or less, right? That's within what we consider our rejection region. What we consider our rejection region. Well, why we set that 5%? See, the thing is when we're collecting samples, these samples can be anywhere, right? They can be really close to our population mean, or they can be really extreme. But our collection of data occurs on days, right? We never know what's going on in people's lives on a given day. Like, let's say I'm looking at happiness and I have a mean happiness, standardized mean happiness is zero. Remember, I converted everything to have a mean of zero, right? So I collect data on happiness. And once I standardize a score on the sample, it's 1.964, right? That 1.964 is further away than 1.645. So this has less than a 5% chance of occurring if the null hypothesis is true, right? Because any value within this region here has less than a 5% chance of occurring. Now, here's the interesting thing. Let's say I collected data on the sample the day after, say, the Eagles won the Super Bowl, and I was collecting data in Philadelphia. People would be pretty happy. So this 1.964 may not be a real indicator of happiness. It may be a consequence of the day's events. So that's the randomness of sampling. We can't control for all these events that can affect a person's life. Or maybe somebody's a big Carlos Alcaraz fan. He won the French Open, 2025 French Open yesterday. So they may be really happy today. So you never know why a person responds the way they do. And that's one reason why we have to do studies over and over again, because our samples can be accidental. But to ensure that we have the best probability of accounting for that randomness, we set our criterion to be pretty extreme, right? 5% or less. That excludes the 95% of all values, right? So to consider something statistically significant and to account for that randomness, we say, okay, I'll accept being wrong. I might be wrong because of this randomness in my sampling, but the probability of me being wrong is less than or equal to 5%. And in this case, it'll be even smaller. It'll be the actual probability beyond 1.964 is about 2.5%, right? So it's going to be very, very small, and I can live with that. So we have to have extreme cutoff values. And that's why, again, why in some cases we go to an alpha of 0.01, because we have to deal with the randomness of sampling. Okay. Now, if on the other hand, I didn't do a one-tail test, like I didn't pick a directional hypothesis, let's say instead we did a two-tail non-directional. So instead of saying that, well, my null hypothesis was that my sample mean is equal to the population, my alternative is that my sample mean is greater than the population mean, and I set my alpha at 0.05, but instead now my alternative hypothesis is that my sample mean differs from the population mean. So what that would mean that is that the sample mean could either be greater than the population mean or it can be less than the population mean. But I have to keep my alpha at 0.05, right? That's what I set it at. So I have to split that uncertainty in half. So half of 0.05 is 0.025. So you'll notice that when I do that, my cutoff point shifts from 1.645 to positive 1.964. So it's moved further away, right? And then also by symmetry, I'm moving my cutoff in case my result is negative from minus 1.645 to minus 1.964. So what I've done there is I've actually made it more difficult to reject the null hypothesis. Because in order to reject the null hypothesis, my calculated value has to be further than 1.964. Earlier, it just had to be further than 1.645. But now it has to be further than 1.964 or further from the mean than minus 1.964. So by using a two-tailed or a non-directional alternative rather than a one-tailed, not only have I shifted the critical values, I've made my life more difficult and I've lost power because the probability of rejecting the false null hypothesis has become harder. So I've done a lot of damage to my aim. It doesn't mean that if it's a good study, you may reject it regardless, right? But understand though when you're designing studies that you want to take that into account, right? One versus two tail. Why do people do the difference? So if I'm not really sure if there will be a difference in a specific direction, a two-tail test makes more sense. If I am sure, a one-tail test makes more sense because it's more powerful. That's pretty much why we make those choices. One thing you can't do is change things after the fact. Like if something could be significant in one tail but not significant in two tail, right? Just because of the way those critical values moved, you can't change it after the fact. Oh, well, it's I meant all along that this was a one tail. No, you can't do that. That's that's bad research ethics, violation of research ethics. Now you could say that this approach significance two tail, and if this was a one tail test, you could probably say that I wouldn't kill anybody, but you can't change it. All right, let's look at sample size and power because I mentioned power and I mentioned how it's important to calculate your sample size. Sample size and power are related. The higher the sample size, the greater the power, right? This has to do with our standard error. So when we collect all these samples, let me go back here. When we're collecting all these samples from the population and we plot the distribution, plot the means of all these samples, we get the population mean. We'd have like a plot just like this. This is a plot of individuals, right? We can do also plot samples, right? So this is the sampling distribution, right? Sampling distribution of the mean. The mean of all the sample means is the population mean. The standard deviation of the sample means is what we call the standard error of the mean. It makes logical sense that we have to divide our standard deviation by the square root of the sample size. Well, actually, let me just make that's not as logical. It's logical that we divide the variance, right, the variability by the sample size, right? So in a sense, we're weighting the calculation for the sample size, weighting the variance for the sample size. Now, if we so let me go back to that equation. So if this was the variance, it would be sigma squared divided by n, but the standard error is the standard deviation of the sampling of the samples, right? The sample mean. So standard deviation is the square root of the variance. So that's why when we take the square root of the numerator and the denominator, we get sigma divided by the square root of n. So that's how we get that. But one thing you'll notice here is that the standard error is affected by the sample size. So the larger the sample size, the smaller the standard error, just because we're dividing by n, right? So let's take a look at it, what the effect of this is and why a larger sample size increases power. Man, I love this stuff. I hope you like it too. Or, otherwise I'm just talking to nobody. Well, Piper's listening. My parrot is listening to me, so that's good. All right, so here's the population. And this is standard normal distribution, right? Mean of 0, standard deviation of 1. Here's my standard error, sigma divided by the square root of n. I have, in this case, a negative z value. Good thing I'm picking negative because I want to make sure you're used to all views, right? So 1.68, that's my cutoff value here. Alpha of, I believe this is, I don't know what that, I'm not really sure what the alpha is here, but it's z of minus 1.68. This alpha of 0.05 is 1.645, but I picked 1.68. So this is our cutoff value right here. Okay, so now here we have a sample of 20 individuals, and we have a standard deviation of 1.5. So using this equation, the standard error is 0.335. So if we look at our sample, this is our sample, right? You'll notice that a large proportion of the sample is to the left of our critical value, our cutoff value. Any sample falling within this region would reject the null hypothesis, right? By definition, because the probability it has to have a p-value less than or equal to whatever it is, well, less than or equal to 0.05, right? So it'd have to be in this region. So any sample within this region here would be considered statistically significant. Now look what happens if I increase my sample size up to 30. My standard error shrinks. So shrinking the standard error literally means that this distribution gets smaller, narrower. The tails are coming closer to the mean of this, right? Right. Notice when that happens that a greater proportion of samples, and it's weird that I say samples because you think, well, why are you saying samples when you're talking about one sample here? When we're doing statistical testing, we want to test to see if our sample is representative of a different population. So in this case, this could be its own population with samples picked from within there. So think of it that way. But notice that a greater proportion of samples would be to the left of this cutoff point. So let's say this is I don't know, 80%, and now we've jumped up to 95%. So what we've done, we've increased our power. That proportion, 80% is the power with 20 individuals. If our sample size is 30, our power jumps up to 95% or something like that, because the majority of that curve, the area under the curve is to the left of our critical value. Isn't that cool? Let's explain. So that's why I like, it's funny though, the reason I had a student in research methods who asked me for specifics, like why does this exactly happen? Or why is beta related to why is beta related to alpha? Can you be specific? And I love that question. Well, here you can see why it is right here, okay? So beta is the inverse of power, right? So your beta is right here, is larger, and your beta here, or beta is the type 2 error probability. It's larger here, smaller here. That depends on where your alpha is, right? So your alpha will determine where this critical value is. So your beta is related to alpha because your beta will be determined by your alpha in this case. So whatever you choose as your cutoff point, that's going to affect probability of failing to reject a false null hypothesis. Bam, I love it. All right, so what else? Da-da, you got that, you got that. Let's talk about effect sizes. We're talking about the different elements for calculating power, right? We talked about alpha, we talked about power, effect size. So these are just an attempt to make something that is non-standardized, standardized. So really to know if something is effective, has a strong effect, excuse me, has a strong effect, I should say, you really need to ask people, right? Hey, did this help you get better? Yes. Or you need to talk to a clinician. Clinicians know what is a good effect size. Statisticians don't know. Only the clinician knows. So the idea was, well, let's see if we can create something that would allow us to standardize effect sizes. There are a couple of popular statistics that are used. One is Cohen's d, and the other is the correlation coefficient. So Cohen's d is just a standardized difference between means, like two group means, like the experimental group versus the control group. We take the mean difference, and we have to have this standard error. We use something called a pooled standard error in calculating this, or sometimes you can use one of the different, I don't know, one of the standard deviations from the groups. But Cohen's d has the following heuristics. A small effect would be zero point 0.2, somewhere between zero point 0.2 and zero point 0.5. A medium effect would be between zero point 0.5 and zero point 0.8, and a large effect would be greater than or equal to zero point 0.8. I'm sorry for using the GE there, not General Electric, but greater than or equal to. In terms of correlation coefficients, I'd mentioned before when we talked about correlations that correlations are effect sizes. So there's small, medium, and large correlations. Small correlations between zero point 0.1 and zero point 0.3. Medium is between zero point 0.3 and zero point 0.5, and large is greater than or equal to zero point 0.5. So we could use those. One of the statistical packages that's freely available and you can download it, you should download it, and want to use it for your proposals, is Gpower. So this is a freely available software that helps you calculate most of the powers that you need. Not all. There's some that you have to run other kinds of analyses. Like I run simulations sometimes when I do complicated power. We call these power analysis. In terms of Gpower, a couple things you want to know when I think I have pictures. Yeah. Yes. Well, you're given the option to select small, medium, or large. Clearly, large effect sizes, those are good in that they will really re increase your power and reduce your sample size. However, you have to have a lot of evidence to use a large effect size. If you use a really small effect size, that's going to really increase the sample size you need. In most situations, it's best to select a medium effect size. Now, sometimes it's better to power for a small effect, but the problem there is that it's going to cost you a lot of money to collect really large sample sizes. You got to be very judicious in how you deal with effect sizes when you're determining power. So here's an example. A researcher is interested in studying happiness in traditional college students ages 18 to 22. The result of a recent study suggests that the population mean on happiness among traditional college students 18 to 22 is 170. What sample size would we need to detect a difference in 20 points, assuming that there is a sample of very happy individuals scoring 190 with a standard deviation of 40. All right, let's go ahead and get started here. So in this case, I said detecting a happiness. What's so there's population mean happiness among traditional colleges. So we were looking for 190, right, versus 170, so 20% greater. So we'll do one tail because again, we're talking about a direction. 190 is greater than 170. Okay. So we have select a one tail test. And let's stick with 0.05. There's no reason to do, let's just do that. That's the traditional one. We also selected a medium effect size. I'm not going to go to a large or small. So medium effect size. And this is using Cohen's D because we're talking about a mean difference. We'll do 0.05. I mean, zero point 0.5, excuse me, as a medium effect size. But you don't even have to put that in. In general, when you use Gpower, here's a screenshot of Gpower, right? And this case, we're looking at t-tests. So this is the t-test family. Difference from it's one sample case because we're dealing with a population versus a sample. So it's a one sample t-test. So, and before I show you this, talk more about this, we also select a power of 0.8. Power of 0.8, that's pretty much the traditional power you want to select. It's an 80% chance of rejecting a false null hypothesis. If you go beyond that, you're probably you're going to make your life a lot harder. So in general, in research, especially in grant research, which is struggling right now due to government restrictions, but generally to get a grant, you want a power 4.8. So that's just the minimum power that you want. mean, again, you can be power 100% chance of rejecting a false null hypothesis, but then you're probably going to have a really, really large sample size, need a really large sample size. All right, so this is Gpower. Gpower, it's a computer package that spits out these really beautiful statistics. So you select everything in advance. So you select your effect size. In some cases, if the statistical analysis that you're looking at, and there's various statistical analyses available, if it's well known, like in this case, it's a mean difference. So it's going to tell us we want Cohen's d, and if you hover over this, it'll actually show you the heuristic small, medium, and large, so you can pick the right one. And the default is medium, so it always defaults to the medium. Your alpha, you select that on your own, and then your power. It'll sets it up, I believe, by default at 0.95, but no, never use that. Go straight to 80, 0.80. Then you tell one or two tail test. Now, it has a family of tests, so you have to understand what the tests are. Like if I'm doing a t-test, obviously I'm going to pick t-test. If I'm doing a z-test, obviously I'll pick z-test. If I'm doing an f-test, I'll pick f-test. But sometimes certain statistical analyses methods use different types of tests. Like for instance, if I'm doing a regression analysis, regression analysis uses t-tests to assess the individual effects, like what's the effect of this predictor on the outcome. However, if I'm looking at the entire model, it would use an f-test. So you'll choose the family of tests and then you choose what you need from that. But you have to know that, for instance, the overall regression is looked at with an f-test, right? That's like testing the overall model, and then individual effects in a regression would be t-tests. But so in that case, you kind of have to know in advance what you're doing, at least have an understanding of the different types of analysis. When I'm computing sample size, I look at a priori, that's before the fact. But sometimes I want to calculate my power. Like, what is my power? That's posterior. That's after, right? So you have that option. So you can say, do I want a priori or after the fact? So this is a priori because we want the sample size. And then once we click calculate, it'll provide us with all the information we need, right? Really what we're looking here is our sample size. That's what we want more than anything. It says we need a sample size of 27, and our actual power with that sample size would be 0.81. That's what we want. However, I could have calculated the seats versus determine instead of picking the effect size by just guessing it or something like that. I may have data, like in this case, I have data and I can just plug it in to this. After pressing determine, I can plug it in. Here's my null mean is 170. That's the population mean. Here's my alternative mean. That's based on my sample and its standard deviation. And it'll calculate the effect size for me. And here was 0.5 and it's plugged in zero point 0.5 anyway. So it can be done that way too. So that's Gpower. And then Gpower gives you all these really nice, in addition to this, it gives you these really nice figures. Like it shows you where your critical values and it shows you the beta and the alpha. So you can see like where the student asked me about the relation, it shows you everything here, right? Here's your alpha, here's your beta, here's your critical value, right? That's pretty cool. And then here, if you want, and I like this a lot, it gives you this list of, okay, what would happen with different sample sizes given alpha of 0.05, Cohen's d of that, etc. So if I had a sample size, so it's a 27, I get zero point 0.8. If I have a sample size of 30, I'd get 0.85. If I have a sample size of 36, it'll be 0.9, and so on. That's pretty cool, right? So you can know and select things appropriately. All right, let's talk about different types of sampling. So there are different types of sampling. Random sampling is the most coveted type of sampling. That's one we'd like to do. So each individual in the sampling frame or the population from which we're deriving our sample has an equal likelihood of being selected to the sample. That's really great. That in simple random sampling, that's simple random sampling. Each individual has an equal likelihood of being selected into our sample. The benefits of random sampling is that it ensures ecological validity. In other words, that our sample is representative or generalizes to the population. We also have other types of sampling, random sampling. There's stratified random sampling. In stratified random sampling, we divide our sample into strata defined by important characteristics such as race, ethnicity, education. So we could divide our, say, I don't know, divide it into African American, Caucasian, other race. So we can divide it, and then we can randomly sample, use simple random sampling within each of those strata. So this still ensures not only do we have a nice representative sample, but it ensures that we have representation of smaller strata. So sometimes, even though we do random sampling, there's no guarantee that our sample will be representative of the population. So this just helps ensure it. You also could use cluster random sampling. So this occurs when we have no access to our sampling frame. For instance, when you're dealing with schools and school districts, we may not have access to our sampling frame, so we can't randomly sample. If we did, we could just use simple random sampling. Like if I had every student in a school district, their names and information, then I could randomly sample from within. But usually we're not given access to that because some of the data are protected. So what we do is we create sample clusters. A cluster could be different high schools. So we instead of picking randomly sampling a student, we randomly sample a select number of high schools from within a school district. So these are our clusters, right? And then we can also, within these high schools, we can use cluster sampling and randomly sample classrooms from within the high school. But then we can go into finally we can go to our individual unit level and randomly select students from within the classroom. So again, so this is another type of random sampling that we do, but it occurs when we don't have access to the sampling frame. So those are both types of random sampling, and then simple random sampling is the third. However, not all sampling is random, and it can't always be random just because we can't do it for whatever reason. We don't have access to the sampling frame. It's just not convenient. And most research uses non-random sampling. So under non-random sampling, we have convenience sampling. So we sample from those individuals we have easy access to. For instance, college students. Most professors in the old days would use college students for their studies because, hey, they have access to college students, and many universities and colleges still do that, especially in psychology programs. You get credit for being a research participant. Could be individuals within your community. Purpose of sampling, researchers sample participants with some specific characteristic, for instance, sampling coffee drinkers to understand the nature of caffeine addiction, sampling individuals with spider phobia to understand how phobia impacts one's daily life. It's not easy to randomly sample these, right? So, because you'd have to somehow have a list of all coffee drinkers or a list of all spider phobics. So instead, it's easier to do convenience sampling here. Quota sampling, you set a quota for some characteristic. For instance, the national proportion of whatever that characteristic is. An example would be sampling nursing students. So we sample males until enough males are reached to meet whatever our quota is, the proportion of males within the population of nursing students nationwide. So you don't always have access to that. But if you do this type of sampling, quota sampling, I could say, okay, well, I need like 10 male. Say I'm picking 100 nurses, nursing students. I need to match the national average. I need 15 male. So I'm gonna try to my best to get 15 male nursing students. When a situation is very complicated, for instance, when we're dealing with special populations, like right now, I'm sure there's a lot of migrant workers who would not want to be identified because they're afraid of being deported. So if I was interested in doing research with migrant workers, there's no way I would put an ad, hey, migrant workers come here, they probably think this is an ICE operation, right? So instead, best way to deal with difficult to reach populations is to use what's called snowball sampling, where each participant identifies another participant. So I have a friend who's, say, one homeless person could identify another homeless person. Heroin addicts could help identify other heroin addicts, transgender females might be able to identify other transgender females, and so on. So we use snowball sampling, but those are clearly not random samples. They're very biased. So that's a limitation in a study when you're sampling like that. My friends, that's all I got for you today. I hope you enjoyed this. Any questions, let me know. And listen, hey, if you haven't subscribed to my channel, please do. Helps me out a lot. I got to get to 500. I'm close, but I'm not there yet. All right. Hit subscribe. It's free. All right. Thank you.